All right, we're back for more. Just got basically two ideas to talk to you guys about today, kind of encompassing three sets of reactions. So the first thing I wanted to talk to you guys about, and I just turned, there it is, okay, is we have been dealing with enolates for this chapter, and we've talked about how to add a halogen to the alpha position. We talked about how to use our enolates to do these condensation reactions, the Claisen condensations, the aldol condensations, these kind of things. The last thing we want to do is how to add carbon groups to our alpha positions, okay? Now, if we take a ketone, right, a generic ketone, put in some kind of strong base, so let's put in some LDA, okay? We know that we're going to end up generating that enolate, right? To some degree, right? If we use LDA, right, then it's irreversible and all this kind of stuff, right? And that's a little bit more useful for us, right? That's kind of previous video idea there, right? Essentially, what we're doing is we put a negative charge at the alpha position, right? So then, if we come in and we add some kind of alkyl halide, wherein that alkyl halide is capable of doing an SN2 reaction, right? Wherein it's capable of doing an SN2 reaction. What we'll end up doing is adding that alkyl group to the alpha position, okay? A couple things to note, right? We add these in separate steps. You don't want to put an alkyl halide in there with LDA, right? Then we're definitely going to start alkylating that N- there, right? Even if it's sterically hindered, right? It's still going to end up reacting with that, and just not fun times, right? So just put them in there separately. So we do this, and there it is. Oh my goodness. And fantastic, right? Ta-da, right? You guys aren't, this isn't that shocking, right? This is stuff that we've already done. But what if now I take this, okay, and I want to do the same thing? What if I want to alkylate this here, right? What if I want to alkylate this ketone? Now we've got a problem, because now we have an asymmetric ketone. If I was doing everything properly before, then all the examples that we were working with before were symmetric ketones, okay? But here's what I mean. Let's say that I add some kind of base. Let's say I add some kind of base and I generate an enolate. I have two options. One, I could generate my enolate here, like such, okay? The other option is, let's use purple, I think that'll stand out, okay? The other option is I could come back and use, or generate this enolate here. You guys with me? Remember, when we're generating enolate, we're just looking next door to see if we got a hydrogen at those carbon positions, okay? So to get to my purple enolate, I have to get rid of my purple hydrogen. To get my red enolate, I have to get rid of one of those red hydrogens. Now, which one of these enolates is better? Now, I'm hesitate to use the word better because that's such a, it doesn't mean anything, right? Better by what metric, by what standard? Well, if we're talking about stability, right, energetic stability, this is the favored enolate. So it goes back to this idea that we talked about when we were first introducing carbocations even, right? We always want to generate, or there's a strong drive to generate the most stable carbocation. That's going to be the intermediate, that's most common in the reaction, right? And that's going to be the more reactive species, right? So what we're looking at here is where our double bond is. So we got our double bond here, a tri-substituted versus a tetra-substituted double bond. So if we go back to this, when we first started learning about alkenes, the more substituted you can make an alkene, the happier it is, right? So a tetrasubstituted alkene is preferred energetically over a trisubstituted. So this is going to be the favored intermediate. But this is going to be faster to form. So this is our kinetic product, and this is our thermodynamic product. So now we go back to these concepts that we talked about a little bit, and I try and always skirt around them just because I've noticed a tendency for, as soon as I say kinetics and thermodynamics, you guys get flashbacks to Gen Chem and everybody, kind of like shudders, and it's a difficult concept. I get it, right? So I try and, not refer to it, but there's really no better term for it. I could say fast and slow or whatever else, but it doesn't really matter. But let's think about this, right? Let's think about this. Why would my red be faster there? Well, I would say there's two reasons, okay? I think I mentioned this in a previous video, but there's always two smart answers you can give in any chemistry class you ever take, right? The two smart answers are sterics and energetics, okay? So if a professor asks you, like, why does this happen? And they call on you, and you just, I have no idea, just guess one of those, sterics or electronics. And you'll be right about 50% of the time, but expect the follow-up question with, what do you mean, right? But the point being, whenever somebody says, well, why would this be more stable? You should kind of default to one of those two questions there. Well, is it sterics or is it electronics, okay? And really, there's two reasons. We know electronically this is preferred, so we can't make an electronic argument here, but we could definitely make a steric argument there, right? So here's what I mean. Let's say that I am using LDA, right? Remember, the whole deal with LDA is it's a big, bulky base. If this is a big, bulky base, it's going to be far easier for it to go after these red hydrogens, okay? Because this purple hydrogen here has got that R group there. We don't know what it is. Even if it's just a methyl group, that green hydrogen is far more, the purple hydrogen is far more sterically hindered than the red hydrogens are. Further, right? These two red hydrogens, there's two red hydrogens for every one purple. So statistically, we could even make an argument that there's twice as many red hydrogens as purple, and going through collision theory and yada, 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 we could say it'd be twice as frequent for that to happen, and that's a fair argument to make also, right? So with a big bulky base like LDA, we would favor this. However, remember, all these things are going to go in equilibrium with each other. So eventually, this is going to equilibrate to the thermodynamic product here, okay? That is something that happens. Except if we shut that down, or shut it down as much as we can, okay? And the easiest way to do it is to cool it down, okay? So if we add LDA, which sterically favors this, and we cool it down, and that's basically saying we're going for the kinetic product, right? Whenever you keep something cold, that means it's low energy, right? Low energy just means, we're going to be kind of trying to push towards our kinetic product there, although that's a generic statement too, right? So we will end up favoring our kinetic product there, okay? However, if I come back and I give a not so bulky base, and I do it at room temperature, so whatever, 25 degrees Celsius, that's perfectly fine, we'll end up forming this product here, okay? I should say this intermediate, not really product. Gotta be careful. And now if we come back in and we add our, let's pick a different color. Let's see, yellow? Yeah, sure, yellow. And now if we come back in and add our alkyl halide, what we will end up doing is forming two separate products. Wherein up here, kinetically, we would form that, and thermodynamically down here, we would form that. Got it? So we can choose now, essentially just based off of temperature, right? Where we can add our second alkyl group to an asymmetric to an asymmetric ketone, okay? Extremely useful. Making carbon-carbon bonds, very powerful to know, right? How easy is it for us to make alkyl halides at this point? It's a piece of cake, right? And so just kind of combining these ideas together, and then we can end up adding our alkyl groups to different positions around the ring, right? Fantastic. There are some limitations with this though, okay? The limitations are, still in both cases, we have to use powerful bases, okay? And if we've got, other functional groups around that aren't as tolerant, then, we've got some side reactions or things that we got to deal with, right? But that's okay, because we can use some other, let's say, ideas here, right? We can use some other ideas here to add some alkyl groups. All right. So now, let's say that we have this guy, okay? An alpha beta unsaturated ketone. Just for fun. Okay, just for fun, can you guys make this starting from here, right? So always good practice to kind of, put together some of these synthetic strings here to come up with our product, our starting materials. But anyway, right? So see if you guys can make that. So we've got this alpha beta unsaturated ketone here. Let's say I add some kind of nucleophile to this, okay? I add something negative. Well, where's that nucleophile going to go? Well, there's two options, okay? The two options look like this. I could, right, draw a resonance structure wherein my positive charge is directly on that carbonyl carbon. This isn't too shocking. This is what we've been doing so far, right? Remember when we're trying to figure out a reaction, you always got to want to look where your negative and your positives are, right? And so my nucleophile could add to that carbon there, and that wouldn't be anything surprising, right? This is something coming in, we open the door, then we got to check whether we close the door, and blah, 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 all the stuff that goes along with that, right? But there's another option, right? What color is going to show up best? Maybe black will. Okay. The other option is this, wherein, we can put a positive charge at the 4 position. Okay? So we would call this at the 2 position, this is at the 4, right? 1, 2, 3, 4. Right, 1, 2, 3, 4, right? So we have 1, 2 versus 1, 4 addition. So this is something we talked about also in a previous chapter, right? And so the nucleophile can also add at the 4 position. Well, how do we know whether it's going to add at the 2 or the 4? Well, this comes down to the nature of the nucleophile. Not all negatives are the same. This is not a shocking concept to you guys either. Because if I said, describe the reactivity of the iodide anion, so I minus, and contrast it to the fluoride anion, F minus. There's a huge difference in reactivity between I minus and F minus, right? And it comes down to, or we could simplify it into the concept of hard, soft, acid-base theory. Now the reason why I just wanted to briefly mention this is because for any of you guys who are moving on to inorganic chemistry, and even if you're just moving on to biochemists, I don't think they really use that terminology, but the idea is all going to be there, I promise, okay? But especially if you're going on to inorganic chemistry, you're going to talk about hard, soft, acid-base theory, right? It's one of the first ideas that I talk about with my students when I go through inorganic chemistry with them, right? But anyway, let's say we don't want to learn a new terminology. I don't want to talk about hard, soft, acid-base theory. It's squishiness, right? Now, squishiness doesn't sound scientific, so we don't want to write a scientific article saying, well, we've made a new squishy anion. So we call it polarizability, right? Which just comes down to spreading out a minus charge. A soft minus charge is a polarized or spread out minus charge. That's all we're talking about, okay? So whenever somebody says a hard or soft acid or base, we're just talking about how polarizable it is. In general, of course, there's other ideas behind it too, right? But if you just kind of remember that idea, then you'll be right more often than you're not, right? Which is always a good place to be. So we have two tasks then, right? We have to understand, or really, excuse me, we only have one task. We have to understand the nature of the nucleophile. And that's going to be easy for us, okay? Let's give the example, I guess I should say. Yeah, I think it might be best if I do this down here. Yeah. I was trying to add everything together in one picture, but I think it would have gotten too cluttered and too much erasing to do. Mr. Grignard comes in, MGBR. You'll pardon my somewhat cruddier than normal handwriting. My pen is starting to break, so and the new tips haven't come in. So sorry. I hope I always post. I will post my notes once I'm done recording all the videos. So in case you guys are like, what in the world? So but anyway, just always feel free to just contact me if you can't read what it is. But anyway. Mr. Grignard, we've used these quite a bit. And we already know what's going to happen, right? We've got a ketone. We have got an extremely powerful base / nucleophile, right? We know that this is going to add at the 2 position, right? And remember, whenever we Grignard it up, we always want to do some kind of acid or water workup at the end. Either one is just fine. I'm not going to be picky about that. And our double bond is still there. Cool, right? Nothing too shocking there. We attack the carbonyl carbon, we swing open the door, we can't close the door, so it's stuck at the alcohol, right? Good stuff. Now we really shake things up. Now instead of using a Grignard, let's use a Gilman reagent. Or, I guess just for completionist sake, right? We can, cool, sounds good, okay? Now, what's the difference? Well, in both cases, we essentially have an R with a minus charge, okay? We don't really care about the MGBR too much. It's there as a counterion and blah, 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 and there's, the Schlenk equilibriums and all this other kind of stuff that goes with it. Very important, but anyway, right? The point being this, the alkyl group is bound to a copper versus a magnesium. So how minus that carbon feels is very different. To the point that these R's right here, these Gilman reagents, are not going to react with ketones. Oh, we've got a very selective alkylating group here. That's pretty darn important. So softer negative, harder negative, right? More polarized, less polarized, that kind of idea. So what's going to happen here, if you'll allow me to simplify for a minute, let's say we just have R minus, okay? So this is going to come in here, hit at the 4 position, and we'll follow that cascade of arrows there. With me? We add at the 4. What do we have here? Well, we have an enolate. What do we know about enolates? Well, they're going to tautomerize, right? And so at the end of this, what we will end up with, right, after our tautomerization, right, is that. Fantastic. We can add an alkyl group at the 4 position now. That's great. Okay? All we need is a nice, soft minus R group there. Now on page 988. Okay? On page 988, they give you guys a list of donors and acceptors. Now what this is it's a Michael addition is what they call it. Okay? Whatever you want to call it. Conjugate addition, Michael addition, all this kind of stuff, right? I'm not going to be too picky about that. So on page 988, they give you a list of Michael donors. Really, there's 2 things I want you guys to get out of this list, right? Take a look at the minus charge on that list. You'll notice that in all those cases, you can draw a lot of resonance structures to spread out that minus charge. That's the important part, okay? That's the polarized minus charge. That's the squishy, that's the soft minus charge. But if you take a look at that list, you see they're very unusual reagents in the sense of they seem very specific, right? With the exception of our Gilman reagents here. Now, you guys know how to make Gilman reagents. You start with the alkyl, you make the lithium, you add the copper, and you make your own Gilman reagent. Pretty darn easy to do, right? So we can make any R group here that we want to. That's very useful, okay? Whereas with the other Michael donors, it's just kind of very specific, but I'm not saying inconsequential either, right? But the idea is you can add at the 4 position with a softer minus charge, okay? But we've got a couple of, we've got another reaction to learn here, and that's the Stork enamine, what do they call it, Stork addition or Stork enamine synthesis? Oh my goodness, okay. I'm really bad with names if you guys haven't figured it out by now. I always got to look that stuff up. Okay, LDA, we're trying to make a enolate. Is an enolate a soft minus charge? Right? Now if we take this, and let's say we add in a alpha beta unsaturated aldehyde there, or ketone, okay? This won't react. What we're trying to do here, or what we were hoping would happen, is we put a minus charge there, and we were hoping something like this would happen, where in our product, let's see, 1, 2, 3, okay, would be this. That doesn't work so well. We've got to, the enolate there and the minus charge just doesn't kind of, everything just isn't kind of clicking together. But what we can do is this instead, right? And so here's the Stork addition. What we do first is add in a secondary amine. With me? You need 2 R groups and you need to have at least 1 hydrogen. Okay? That's important. You need to have only 1 hydrogen, 2 alkyl groups on there. I don't really care what they are, right? Now when you do this, in the presence of some acid, some aqueous acid, what you'll end up making is the imine, right? Okay. Oops. Now we learned about this when we were talking about our ketone reactivity. I don't remember all the way back then. Watch. What do we have? Acid, ketone, nucleophile. How does this mechanism proceed? Very good practice to stop here and see if you guys can get to the product. Okay? But watch what happens. Now we can push a mechanism to put, or excuse me, some arrows to put a negative charge here at that alpha position. And this is a much softer minus charge. This is a fantastic donor to do 1,4 additions. Okay, so what we in essence did, watch, this is important. What we in essence did was take a ketone and turn it into a fantastic Michael donor. So we can add this, right, to our alpha beta unsaturated ketone, okay? And if we kind of freeze it in time, and if we kind of freeze it in time, we have this going on, right? You guys with me? Right? This attacks here. We have the double bond. We kick up to a minus charge there, right? And if we come back and we do an acid workup with everything, The acid workup does two things. It'll take care of the tautomerization, and it will hydrolyze that imine there back to the original ketone, which is just absolutely fantastic. Now we have this. So what is the utility? Extremely mild conditions. This is a shift, essentially a shift base is what it is, right? Extremely mild conditions to set up a fantastic donor for a 1,4 addition. It is very, very, very simple to string together and make large molecules with this store condition, right? It's a very, very useful methodology for us to do, okay? Plus, you guys know all the mechanisms for this too, right? We learned the mechanism to make our starting, amine complex there, and then, this is essentially the mechanism to do our 1,4 additions there. So good stuff. And there it is. Here's some more good news for you. We are essentially done with chapter 21. There's a couple of things that I didn't talk about in here just because I find them to be extremely specific for certain reactions. Besides, you guys always have your books with you, right? So it's there if you guys do need a reference back to it. But the main ideas are just how do carbonyls react, dealing with the alpha positions, what different functional groups can be put at alpha positions. We learned how to alkylate them, we learned how to halogenate them, we learned how to eliminate them, then we learned how to add at the 4 positions and at the 2 positions, right? So there's a lot of chemistry that comes out of this. Starting on page 999 and all the way through 1,000, right? So 999 through 1,000, or even 1,001. So almost 3 pages of reactions are listed at the end of this chapter. That's always where I recommend you guys start. You take a look at that and say, do I remember how to do all these reactions? Can I explain them, this kind of idea, right? So definitely take a look at those. Okay? But that's it for chapter 21. Chapter 22 is next, and there's only, honestly, I think maybe one or two lectures are going to come out of that. Okay? I'll see you guys next time.